There, my friends, welcome back to Sciencing Around Thermodynamics Part 2. Let's talk about the kinetic theory of gases. That is the remaining part of the thermodynamics. Of course, you know what is ideal gas law, PV equals to nRT, and if you don't know it now. So moles equals to mass upon molar mass. Of course, so volume equals to V by N. Everybody knows that. Come on. So R equals to this. Oh, everybody knows this too. R equals to 8.314 joules per mole Kelvin, 0.0832 atmosphere per mole Kelvin, and 1.96986 calories per mole Kelvin, where Boltzmann constant K is 1.38 into 10 power minus 23 joules per Kelvin. Now let's come to velocities, the main part of the kinetic theory of gases, that is the average velocity. Simple as we take the average of any number in statistics or anything, that is the mean v1 plus v2 plus v3 plus vn upon n. That is n is number of molecules, of course. N is number of molecules, my friend. Calculate those by Avogadro number and all that stuff, and you can just find out average velocity, which is average speed, under root of 8 RT upon pi m. Under root of 8 RT upon pi m. What can you do here? See, I just substituted the values. I got this thing under root of 1.59 RT, 1.59 under root of RT upon n. I'm sorry, but that's not the matter. You should not look at these because these are not easy to remember, but this is because under root of 8 RT by pi m is quite easy to remember, of course. So, and what is RMS velocity? Root means square velocity. V1, V2, V3 are velocities of all the molecules till Vn. Then V1 square plus V2 square plus V3 square. The squares of all these divided by its number is nothing but the RMS velocity. And what are these? You'll hear. Have you ever heard RMS word in electronics? RMS current, what do we say in alternating current? I may tell you, or I will explain you better in the alternating current chapter. For now, RMS velocity equals to under root of 3 RT upon pi m, which is under root of 3 RT upon pi m. What is R? R is 8.3. 3 into 8.3 would be approximately 25. So taking 25 out, it would equal to under root of 5 root of T by m. It would be the RMS velocity. Oops, I forget most probable velocity here. It's 2 RT upon pi m. 2 kT where k is Boltzmann constant. 2 RT upon m. Sorry, not pi. Now what is value of R? 8.314. Multiply it into 2, we get approximate 16, because if you're solving multiple choice questions, you have to do this kind of shortcut things. So what do we get? Take 16 out, 4 root of T by m. So most probable velocity 4 root of T by m, RMS velocity 5 root of T by m. Now velocity of sound in the gas, gamma RT upon m. I would just explain it better to you in the chapter of sounds, waves and sounds. For now, just gamma RT upon m, where gamma equals to Cp upon Cv. I'll tell you afterwards what is this. Ke equals half mv square. So common. Total translational kinetic energy, my friends, not rotational, pure translational, half of n mv square RMS. That is half of mv square RMS. That is kinetic energy. This kinetic energy is here, half of mv square into n, where n is the number of molecules, of course. So number of molecules into kinetic energy gives the total translational kinetic energy. So that's it. Now let's get down to the next page. Now you must be seeing a table which is written degree of freedom. Now what is degree of freedom? Now listen to me carefully. In the language of thermodynamics, degree of freedom is any, listen to me, it's any parameter like temperature, volume or pressure which can be altered without disturbing any other parameter. That is nothing but degree of freedom that relates translatory and rotatory motions of the, molecules or any other atoms or substances. That would be for monoatomic substances, diatomic substances or polyatomic substances. That is for monoatomic, there will be three translatory motions and 0 rotatory motions. Total would be 3. For diatomic, there will be 3 translatory and 2 rotatory, as it's diatomic. So there would be total 5. And for polyatomic, 3 and 3, the total would be 6. I hope these numbers you would learn quite easily. So there was with degree of freedom. Now let's get to the laws of thermodynamics. Now what does the first law tells us? That dq equals to du plus dw, where q is change in heat and u is change in internal energy and w is the change in work. Now I'm just teaching this thing for the people who solve MCQs or multiple choice questions. Some people who'd solve simply the board examinations, it would not be useful for them, and they are not useful. I know they must not waste their time doing these things. They should actually practice for multiple choices, because that decides their rank, their all country rank. So let's do first law, which tells us change in heat equals to change in internal energy plus change in work. That is dq equals nc dt, or this formula, du equals to f by 2 nr dt. This is the formula for internal energy. Volume equals to constant cv, or so cv is the actually specific heat with constant volume. That is f by 2 into r. For monoatomic 3 by 2r, diatomic 5 by 2r, and polyatomic 3r. And at pressure constant, the specific heat would become Cp. It would be F plus 2 upon 2 for monoatomic 5 by 2r, for diatomic 7 by 2r, for polyatomic 4r. Mayer solution, quite important my friends. Cp is given, and if you want to find Cv, then you can use this. Cp equals Cv plus r. Means the difference of Cv upon C, or Cp and Cv difference simply depends on r, that is the gas constant, and nothing else. Ratios of specific heat, which is gamma, I told you in the speed of sound. So gamma, ratio of specific heats, it's Cp upon Cv, f plus 2 upon f. So substituting those values, we get 5 by 3 for monoatomic. You can see right here, 5 by 3 for monoatomic, 7 by 5 for diatomic, and 4 by 3 for polyatomic. So F equals to degree of freedom. I told about degree of freedom, right? So F equals to 2 upon gamma minus 1 for anything. Cv equals to R upon gamma minus 1, and Cp equals to gamma R upon gamma minus 1. For isochoric process, the pressure always remains the volume always remains constant. So dq equals to ncv dt, since volume is constant, cv dt. For isobaric process, dq equals to du plus dw. I don't know why did they take this, but work equals to nr dt. We know that work equals to nr dt, since the pressure is constant. For isothermal process, the pressure would change. So would the volume change, but pressure lies inversely with volume. Pressure relates inversely with volume. So in an isothermal process, work equals to minus of 2.303 nRT log of P1 upon P2. If we would remove this 2.303, we would get ln. And to convert that ln from log, we have to do minus 2.303. So minus of 2.303 nRT log of P1 upon P2, or minus of 2.303 nRT log of V2 upon V1, as you can see. And for adiabatic process, the process where the heat remains constant, the heat change remains constant, where work equals to P1 V1 minus P2 V2 upon gamma minus 1. Since it's adiabatic process, its pressure would change, volume would change. Here pressure and volume are just taken their products at the same phase, that is P1 V1 minus P2 V2 upon gamma minus 1. Of course, for adiabatic process, PV power gamma is equals to constant, PV power gamma, where gamma equals to Cp upon Cv. So PV power Cp upon Cv is always constant for adiabatic process, because the heat is constant. So the gamma would approximately be constant, or we shouldn't say approximately, but pressure and volume power gamma would be constant, nothing else. Last thing, don't look at these. dP upon dV in adiabatic process equals to gamma into dP upon dV into isothermal process. That is, change in pressure upon change in volume at any adiabatic process is change in pressure upon change in volume in any isothermal process multiplied by gamma. Now let's get on to our next page. So guys, we are on our last part, that is the molar specific heat. What does this say? Molar specific heat. At the beginning you must have heard that in my last video. In this, PV power n equals to k, where k is the constant. I didn't write constant, fuck me. PV power n equals to constant. So efficiency, now we have efficiency, simple piece of shit, don't look at it. Efficiency can be also told as eta in any cyclic process equals to work upon input energy, or we should say input heat. So equals to 1 minus output heat upon input heat. You get a sink here. I would just make another video to explain you, because it's quite a large topic, and it's not actually the thermodynamics topic. It's actually the topic of, what do we say, of it has some other topic. I would explain this with along with the heat transfer, but for now I don't want to make video long, so let's end it here. So guys, I hope you like the video. If you like this video, then please do like and subscribe, and please leave the comments of how did I teach and what should I do to improve myself to just earn your subscription. Thanks guys, see you next time, goodbye and happy sciencing. Hope you learned something.